Good morning to everyone. My presentation will be on the seismic behavior of slab-column connections using high-performance fiber-reinforced concrete. The motivation of this work was that punching shear reinforcement like stirrups or headed studs had already proved to be a viable solution to improve the deformation capacity of slab-column connections under seismic actions. But new materials are being developed, and we, inside the project, developed a high-performance fiber-reinforced concrete that has better tension and compression performance than conventional concrete, and tested in these connections. So this presentation will be on the test that we made using this material near the column, and the test results will be compared to conventional concrete slabs with high strength concrete, and slabs strengthened with headed studs also. Let me just go here. As you can see, our slab model is a model with 4.15 meters per 1.85 meters. The thickness of all the slabs are 15 centimeters, and we have a square column of 25 centimeters. In the slabs, when we used the high-strength concrete or the high-performance fiber-reinforced concrete, we only used these materials near the column in the critical zone, and our slabs were designed to represent the area between middle spans. So these north and south borders are middle spans of the flat slabs. In the right, you can see a slab ready to be tested. In this picture, we can see the horizontal actuator back there, connected to the column. Then we have also the vertical jacks to apply the gravitational loads in 8 points. And here we have 2 subsystems to apply the boundary conditions that we'll show you in the next slides. So our test setup has these 2 subsystems to apply the boundary conditions. The blue system is a system to apply equal vertical displacements in these borders here. So when we have a vertical displacement in this border, this mechanism will apply the same displacement in the other border. And the green subsystem is a subsystem that is rigidly connected to the slab. So when the slab rotates in one border, this will make this profile to rotate also, and will push the other profile in the other side to rotate in the same amount of rotation. Down here we have the vertical load displacement, the vertical gravity load application system in yellow. This system is connected to the column, so when the slab has an horizontal displacement, it will follow the displacement of the slab. Here you can see the subsystems working, the green one to apply equal rotations, and the blue one to apply equal vertical displacements. We used two different amounts of longitudinal reinforcement ratio. In the left, the 0.6, and on the right, 1% ratio. The pictures of this figure has the bottom reinforcement on the left and the top reinforcement on the right. For the bottom reinforcement, we used 10 millimeter bars. For the top reinforcement, we used 12 millimeter bars near the column in the negative bending moment zone, and 10 millimeters in the rest of the slab. So this was our test protocol. We first applied the gravity loads until a target value that was kept constant until the end of the test. And with the gravity load applied, we applied horizontal displacement until a maximum of 6% drift. Here in this slide you can see the first straining solution with headed studs. It was a work developed by Zufi. We had two different layouts in studs. The first with 3 rows of studs and the second with 5 rows of studs. Here you can see a picture of the studs for the 3 rows solution, and in the bottom the same solution ready to be cast in the fair. Here we have the other two solutions that we tested: a high strength concrete and high performance fiber reinforced concrete. In the high strength concrete we cast before the high strength concrete and after the conventional concrete in the rest of the slab, but in the high performance fiber reinforced concrete we had to do in the opposite way, because the high performance fiber reinforced concrete is a self-compacting concrete, so we had to cast first the conventional concrete and then the high performance fiber reinforced concrete. In the right we have all the specimens of these two types. The first specimen that we tested was the high strength concrete only in a 5 centimeter layer near the bottom of the slab. This did work out, as we'll see after. So the rest of the specimens were cast with the concrete in the whole thickness of the slab. Here you can see in this table that all these concretes had similar compressive strengths. The big difference between the high strength concretes and the high performance fiber reinforced concretes is that the fibers will improve the tension response also. As I told you, as you can see, we used only in an area near the column. The high performance fiber reinforced concrete was used in 1.5D from the face of the column, and the high strength concrete was in an area 1.9D, 3.8D, and 2.5D from the face of the column. Okay. This is a big table I try to explain with all the tests. I will start by saying that our gravity shear ratio was more or less kept constant for all the specimens. The gravity shear ratio is the ratio between the vertical centered punching action and the centered vertical punching resistance. This is a very important parameter for horizontal loads maximum displacement. Then for 0.6% ratio we tested 3 slabs, one reference one with no reinforcement, another one with headed studs, and the third one with the high performance fiber reinforced concrete. For 1% ratio we have 6 slabs, one reference one with headed studs, another one with high performance fiber reinforced concrete, and 3 with high strength concrete. In these results, for the 0.6 ratio, you can see that a slab with no shear reinforcement had a poor performance, achieving only more or less 1% drift. With the studs and the high performance fiber reinforced concrete, we were able to achieve the end of the protocol without failure, the 6%. For the 1% ratio, the reference specimen had more or less the same behavior as for the 0.6. Then the studs reached 4% drift, maximum drift, and once more the high performance fiber reinforced concrete didn't achieve or didn't reach failure. For the high-strength concrete, as I referred before, the first slab, only with a small layer in the bottom, didn't work out for the cyclic loading and had a failure for a small drift. The other two solutions reached 3% drift, which is a good drift for horizontal loads. In this slide we have the backbone curves of all the specimens. In the figure on the left, we compare the high-performance fiber-reinforced concrete with the slab with stud. I would highlight here that comparing this green curve with the curve in orange, with the same amount of reinforcement, the high-performance fiber-reinforced concrete had a much higher horizontal load due to the fibers. Okay, so for the high-strength concrete reached the 3% with a lower, also with a lower horizontal load, but a much worse result compared to the high-performance fiber-reinforced concrete. Finally, it's too much light once more, but this is the two slabs with high-performance fiber-reinforced concrete at the end of the tests. So both this and this did not reach failure, but as you can see here, huge cracks were formed on the slab. So with huge cracks, the slab continued to resist. As the main conclusions, we can say that the high-performance fiber-reinforced concrete with a small amount of area near the column had an excellent behavior. The high-strength concrete also had a good behavior, but far away from the high-performance fiber-reinforced concrete. And from our experience, the headed studs can achieve similar maximum drifts, but with lower horizontal forces. Thank you very much.